All right, guys, it's about to get real today. We're going to do related rates. So, what related rates are problems in a single variable. We really have to do a lot of substitution here. And one of the things to remember is that these are problems generally where the rate is the change with respect to time, aka d something, let's say dx dt. So we're going to be taking those implicit differentiation rules with respect to time. Okay, so my rules are you draw the figure or draw yourself a model. Then I want you to remember that everything is going to be written with d something dt. All right. If the quantity is changing, then we represent that with a letter, of course. And then if the quantity is the same, we represent that with a number. So if it's the same all the time, the whole thing, all the time, okay? All right. Next up, look for a secondary relationship between the numbers. So sometimes we can substitute in different equations to help us make the equation easier for us to solve. Lastly, we're going to differentiate and then substitute any values for that we want to evaluate at that specific instance. So one thing, we're going to figure out the volume of a cone. So the volume of a cone is V is equal to 1/3 times pi r squared h. And if we want to figure out the derivative or the rate of the volume with respect to time, we're going to take a derivative. So we're going to take the derivative of v is dv dt. And then I have a product rule situation here. So I have r squared and h squared, and I'm actually going to write the 1/3 pi on the outside because that just seems easier to me. And now I'm going to do the product rule. So I have my left and my right. So it's lefty right, righty left. So left would be r squared times h, which is 1 dh dt, plus right d left. So h times the derivative of the left, which is 2r dr dt. All right, so now we just simplify that. dv dt is equal to 1/3 pi r squared dh dt plus 1/3 pi, sorry, 2/3 pi times RH, my R and my H, dr dt. So this would be the derivative equation for the volume of a cone using implicit differentiation. All right, so we're going to practice before we get some words. So given the situation, we have y is equal to x squared plus 3x, and we're given the rate, which is dx dt of 2, when x is equal to 1. So we know that dx dt is equal to 2 and x is equal to 1. So we want to find dy dt. So we're going to start with our equation. Take a derivative. You want a derivative? Take a derivative. dy dt is equal to 2x. Now, we usually don't have to write anything, but because we're taking the derivative with respect to time, we have to write times dx dt. Yeah. All right. Plus the derivative of 3x is 3 dx dt. The derivative of x with respect to time. All right. So if I want to figure out what dy dt is, then I need to plug in the rate, which is 2, and my x value when x equals 1. Think about this as we're kind of, it's like when we're evaluating the derivative at a point, it's like at what certain time are we evaluating? We're evaluating at 1, okay? So I get dy dt is equal to 2 times 1 from up here, okay? The rate is times 2 plus 3 times 2. That gives me dy dt is equal to 10. Okay? Alrighty. And it's like units per time. So most of these problems, because there's actually going to be units, you can put like units per time, length per time, theta per time. All right, time to get real. Air is being pumped into a spherical balloon at a rate of 4.5 cubic feet per minute. Sorry, at a moment. Find the rate of change of the radius when the radius is 2. So first off, we're going to draw the balloon. Always drawing the balloon. Okay. And it says the air is being pumped into the balloon at 4.5 feet cubed per minute. Okay. Then, which I know is 4.5. So that is, it says the cubic feet per minute. That is the volume, the change in volume with respect to time, dV dt. All right, next up, find the rate of change when the radius. So I know, I always make this list. I know that the rate that the volume is changing is 4.5 feet cubed per minute, cube for volume. And what I want is the radius. I want the change in the radius, so dr dt, when r is equal to 2 feet. Okay, so the radius, even though it's kind of constant, that's when we want to evaluate. It is not, the balloon does not stay at 2 feet all the time, so we cannot plug that in until the very end of the equation. So now I'm going to look, do I have an equation that relates volume and radius? Guess what? I do. I know one. The volume of a sphere is equal to 4/3 pi times r squared. So I want to use the variables that I have information about. I have information about dV and dr, so I'm going to make sure I use those variables in my equation. Since I have I want the rate of r, I'm going to have to make sure I take the derivative. So I'm going to do dV dt for v, and then r is the only variable here. So I'm going to bring down, I have 4/3 pi times 2r times dr dt. Next is, I wrote something wrong. This should be r cubed. Right here, r cubed, making this derivative 3r squared. My apologies. Okay, so the 3's are going to cancel, giving me dV dt is equal to 4 pi r squared times dr dt. Now we're going to solve for dr dt because I know that dV dt is 4.5, 4 pi, and my rate, I'm evaluating at a specific time, like when the radius is 2, and I'm going to multiply that by dr dt and solve. So I get dr dt is equal to 4.5 over let's see, 4 times pi is 16 pi. And I simplify that to give me dr dt. So the radius is changing at a rate of 0.089 feet per second. Or this is truncated, so that means just chopping off the end of the decimal. Rounded is 0.090 feet per second. So either of these are legal on the AP test, truncated or rounded. Okay. Pebbles. Ripples, not pebbles. Yeah, a pebble. Okay, a pebble is dropped into a calm pond, causing ripples in the form of concentric circles. The radius of the outer ripple is increasing at a constant rate of 1 foot per second. When is the radius 4 feet? And at what rate is the total area of the disturbed water changing? So I go through and I just start underlining things. We see we're increasing at a constant rate of 1 foot per second. I'm looking, it says, when is the radius 4 feet? So when is the radius 4 feet? At what, or when the radius is 4 feet, at what rate is the total area? At what rate? Rate. So I'm looking for a rate of area. Okay, so I know I have the change in radius, dr dt, is equal to 1 foot per second. I know I want that the derivative of the area, so the change in area with respect to time, when the radius is equal to 4 feet. Okay, so this information, this 4 feet, is like a save for later when I have more of the derivative figured out. Okay, so what relates radius and area of a circle? Is there an equation that relates radius and area of a circle? And of course, it's area of a circle, so I'm going to use area is equal to pi r squared. You really have to like reach back into that catalog of equations. And I see that I need to take the derivative. So because we want the derivative of a with respect to t times pi times 2r dr dt, implicit differentiation. Remember, we're taking the derivative with respect to time. Okay, so I have dA dt is equal to pi, let's say 2 pi, times the radius that I want to evaluate, times dr dt, which we know as 1. Okay, so dA dt is equal to 8 pi feet squared per second. So feet squared because it's area, feet squared per second. All right, last one on this video. All right, a ladder problem, classic. A 50-foot ladder is leaning up against the side of a building. The base of the ladder is pulled away from the wall of the building at a rate of 3 feet per second. How fast is the top of the ladder falling when the base is 30 feet from the wall? So I have a ladder. It is 50 feet. Is the ladder's length ever going to change? No. Okay. This is the ladder. And the height of the building, it's resting on a building that is like, it could be taller. Okay. And then the base here, the ladder is being pulled away and the ladder is falling down the height of the building. Okay. So I use my 50-foot ladder. I can see that the 3 feet per second, it says, is the base of the ladder is being pulled away from the building. So being pulled away from the building. So the rate that the base is changing the rate that the base is changing is dB dt is equal to -3 feet per second. Okay, up next, I know that the ladder is 50. That's a constant for real. And dB dt is equal to -3 feet per second. I want dH dt, how fast is the ladder falling, when the base is equal to 30 feet. Okay, so looking at this equation, I'm looking at my rates. I have B and H, and I have this here triangle. Is there an equation for a triangle that would incorporate the base and the height? Yes, it is Pythagorean theorem. So I have the base squared plus the height squared is equal to 50 squared. The only reason why I got to plug in that 50 is because the length of the ladder does not change at all. So if the length is going to change as I pull the ladder away, then I would need to use a variable instead of a constant. Okay, so derivative 2b times dB dt plus 2h times dH dt is equal to, the derivative of 50 is 0. Think about it. The ladder is not changing length, so it has a rate of change of 0. All right, substitution. We have 2 times our base is 30 feet, 30 times -3 plus 2 times, oh, wait a second, I don't have anything for h, and then I'm also solving for dH dt. How could I figure out what our h value is going to be? Well, think about what the ladder is going to look at this specific incident. It's going to look like this. I'm going to have my 50-foot ladder with my 30-foot base and my I don't know how high. Can you solve for that? That's a 3, 4, 5 triangle. So this is going to be 40, or you can use Pythagorean theorem to solve. So instead of that height, my dog is going nuts. Sorry. Okay, so 2 times 40, he just thinks he's tough. Okay, because the height when the base is 30 is 40. All right, we continue to solve. We get negative 180 plus 80 is dH dt is equal to 0. So I have 80 dH dt is equal to 180. I know what I did wrong. I can see it. Divided by 80 to get dH dt by itself is 60. Okay, so check it out. Wait, that's not 60. Okay, I got flustered. It's 9/4 feet per second. Okay, so what I did wrong was that the base is increasing in length, so the rate of change would be positive. We okay? So positive. I'll highlight all these. Positive, positive. So I need to change each one of these values to be positive, which is going to give me a positive, which is going to give me a negative. So now I'm going to end up with a dH dt where the ladder of negative 9.4, which makes more sense because the ladder is falling. It's falling. So remember, falling, getting shorter is a negative value. Okay, that's it for this video. I know it's rough.